All right, guys. Welcome to 15.721, database systems. Database systems internals, advanced databases. It goes by many names. I don't know what it says on the register. So I'm passing around two sheets here. So the first is the people that actually are enrolled the class, and the second people are if you're on the wait list. So right now we're maxed at 30 people, and so if someone dies or gets arrested and then a slot frees up, we'll go to the wait list. So just find your name and put your initials, and please only put your initials. I don't care that your friend is at rehab and can't make it today. Just put yours down, okay? All right. So welcome. It's a new semester. So this is the first time this course has been taught at CMU in 10 years. So all the material is new. And it's going to be a lot of work to provide you guys sort of like up-to-date stuff. So normally when I start a new class, I always like to give a quick pop quiz to see what everybody knows to help you motivate why you should take this course. All right? If not, my clicker doesn't work. It would help if I plugged it in, right? Does that work? OK. All right, so here's the pop quiz. 2 questions. Does anybody know who this person is? Anybody? Take a guess. It's not my dad. OK. Anybody know who this is? Who's this? Right. Mark Zuckerberg, the founder of Facebook. Right? This person is Jonathan Abrams. Right? He founded a startup, a website before Facebook called Friendster. Who here has heard of Friendster? Very few, right? When I was an undergrad, before Facebook, before MySpace, Friendster was the hot, the big social networking website. Right? It was Facebook before Facebook. And why do we know the Zuck and not this guy? Right? Why did Facebook succeed and Friendster died? Friendster was there first. Well, when Friendster got started, they started having a lot of users, and their database was struggling, right? So every time you would load the page, this is like talking like 2001, 2002, the database would be super slow because there was too much data and it was getting hammered. One of the things that Zuckerberg did correctly was he hired some really smart people to help them optimize their database system so that they didn't end up with the same fate that Friendster did. Right now, Friendster is like it still exists by name only. Like it's a Malaysian gaming app, right? So part of the reason Facebook was able to succeed where Friendster failed is because they were able to deal with the database problems that they were having, right? They had some really smart engineers, scale the thing out and apply some of the optimizations that we're going to talk about in this class, right? So this is why you want to take 15.721, right? Because databases is still a hot field, right? And database developers, people that actually can work on the inside of database systems, are in huge demand, right? And there's a lot of unsolved problems that are very interesting that we're going to talk about in this class that are still definitely relevant today. And so one of the things that I've noticed, in my time since I've been involved in computer science and things like that, is if you're good enough to be able to hack on the internals of a database system, that has a lot of that holds a lot of weight in the industry. Right? So like if you're like a JavaScript developer, they're not going to have you go write some complex system code, right? But if you can work on the inside of a database system and the internals, right, and be able to deal with writing correct code and high performance code, then you can apply those techniques to almost any other database problem or any other computer science problem. So being able to say, yes, I know how to hack on inside of a database is like knowing how to hack inside the Linux kernel, right? It's a very challenging skill to acquire, and it's definitely in demand. So, all right, so for today's class, we're going to split up in sort of 2 parts. First, I'm going to talk about what this course is going to be about, with the expectations of you are as the student. And then in the remaining time, I'll sort of do a quick crash course on the history of database systems as I see it, right? So we'll spend most of the time at the beginning talking about the course, what's expected and everything, and then we'll end up with something as a prelude for when we start the real content on Wednesday. OK, and so for the people that got in late, there's a sign-up sheet going passed around. There's one sheet is for people that are enrolled. One sheet is for the people that are on the wait list. So just initial your next to your name so that I know that you're here. I'm not going to be taking attendance to the class, just for the first class and the second class, to figure out who is actually here. Okay, so the core idea, the core objective of this course is to learn about the modern practices of database systems. Actually, how do you actually build a database from scratch? Right? What are all the things that you need to know about and care about when you do this? And so we want you as the student to be able to become proficient at the end of the semester to know how to write correct code and high performance code. Right? Those things go hand in hand when you're doing database system work, because you don't want it to be the case that someone writes data 1 week and then they come back 3 weeks later and the data is different. Right? That's bad. We don't want that to happen. So you're going to be working on a large code base for all the projects, which I'll talk about in a second. And so we really care about you writing good code. We care about you documenting your code and applying tests. Right? Database systems are probably the most well-tested software that exists in the world beyond operating systems, and probably like the space shuttle. We're going to spend some time discussing how to do code reviews. Right? So when you do the final project, you're going to be paired up with another group, and you look at their code and make suggestions on what they need to fix, whether things look right or not. We'll apply a lot of the standard practices that are used in industry today. This bullet here about working large code base, when I've been sort of planning this course for the last year, I've talked to a lot of different companies, and I said, well, if you have students coming out of a database internals course from CMU, what skill do you want them to have? What skill do you want them to know at the end of the semester? Right? Do you care about them knowing how to write B+ trees? Do you care about them writing concurrency control? They all basically said the same thing. We care about having students that we hire having the ability to work on a large code base that they didn't write, and that the dude that wrote it has been gone for the last 10 years, and yet you can come in and be able to figure out what's going on and make a significant contribution. So that's sort of what another theme that's going on in this class is that we want you to be able to understand how to, and learn how to adapt to a really large code base that you didn't write and we didn't write, and make significant changes and do the thing that you want to do, right? And this last one here, so most of you here are either American citizens or planning to stay here in the US. So I'm going to spend some time throughout the semester teaching you certain skills that will be useful when you're out in the real world or on the streets, right? How to stay out of trouble, how to deal with the police, things like that. So again, we have extra time in the lectures. I'll spend just a little bit to talk about these kind of things that I think be relevant beyond the thing, once you leave the confines of CMU. And hopefully we're going to get a guest lecturer from a local defense attorney to come and talk to us about some other things that you should be wary of, okay? All right, so again, if you haven't figured this out, the overall topic of the course is about database system internals, okay? And specifically, we're going to focus on single node systems with in-memory databases. And I'll discuss what an in-memory database is on Wednesday. But if you're expecting this course to be about distributed systems or distributed databases, that's not what we're doing here at all. We're going to ignore distributed systems entirely. And the reason why we're going to do this is that, yes, eventually most databases, if you get too big, you may have to go distributed, but you have to be able to deal with all the single node problems that we're going to talk about in this course before you can get to the distributed problem. So for pretty much every single topic in this class, we're going to ignore the multi-node case or the distributed case and really just deal with how do you make a single node shared memory system scale up and perform better. So we're also going to be focusing on state-of-the-art topics or state-of-the-art implementations of these techniques you need in a database system. So that means we're not going to go back and read the papers from IBM from the 1970s and 1980s about sort of the classic implementations of the algorithms and methods and data structures. We're really going to be focusing on the modern incarnations, the modern variants of those techniques. All right. So in general, the layout of the course is roughly as this. So starting next week, we'll talk about concurrency control, right? Because that's a big part of having multiple transactions run at the same time and run correctly. Then we'll spend about a week and a half talking about indexing methods and data structures. We'll talk about storage models, compressions, modern join algorithms to deal with in sort of multi-core, many-core environments, logging recovery methods, query optimization, execution compilation, and new storage hardware. So basically, all of these things here you can combine into a single system, and this will build you a database system. Right? We're ignoring SQL parsing, simple things like that. But all of these techniques is what you need to say, I'm going to have a new single node database system that can do transactions and do analytical queries. You need to do all these stuff. And that's sort of why we're sort of going from the ground up and building all these things out. Okay? So now, I'm making a huge assumption in this course that all of you have the appropriate database background. That means you have either taken 415, 615 here at CMU, or some other introduction database course when you guys were undergrads or somewhere else, right? Because I'm going to be talking about all the classical algorithms that you would learn in that intro course, but then the modern variants of them. So I'm not going to sit and say, here's what a hash join is, here's what a sort merge join is. I'm going to say, here's how you do it when you have 20 cores running at the same time, or everything's in main memory. Okay? I'm also going to be assuming that you have sort of a general knowledge of the architecture of a database system, right? Query plans and things like that. So specifically, the things that we're not going to cover are SQL, serializable theory, relational algebra, and then the basic algorithms and data structures. So if you don't know these things, you should spend some time, maybe read a textbook or talk to me and figure out whether this is actually the right course for you. Okay? Because I'm going to assume you know what serializability means, and we're going to jump right into it when we start talking about concurrency control, or the lower isolation levels. So another big thing in this class is all the projects are going to be in C++11. All right? Because we're working on a new database system we're building here at CMU that's based on Postgres, but we've updated it to be now C++11. And so you'll go in and do all your projects based on that. And we'll provide you sort of scaffolding and sort of instructions how to do the first two projects. But the last project is definitely going to be open-ended, where you'll pick what you want to do. And you'll be off and running in this, parts of the code that we haven't even looked at yet. So if you're not comfortable with debugging a multi-threaded program, like using GDB or other tools, then again, I encourage you to spend some time to figure out before things get started. So maybe start the project early and look at some tutorials and try to understand these things, because I'm not going to teach you how to use GDB in this class, because I'll assume you already know this. Okay? So now the course logistics. So let's talk about now actually what the course is going to be about, what the assignment's going to be, and how you're going to be graded. So all the course policies and the schedule, sort of the reading list and the syllabus and everything, are available on the course website. So you can check out that link. I think it's 15721.courses.cs.cmu.edu. It's on my homepage. But everything we'll be talking about will be here today. And I want to stress this, I'm going to stress this multiple times, is if you're not familiar with CMU's academic policy about cheating, about plagiarism, about stealing, you need to go read this. Okay? So the systems faculty at CMU are actually cracking down this semester. We're not going to be dealing with people plagiarizing and cheating anymore. We're going to definitely report you to Warner Hall. So if you're in a situation where you don't know whether you're doing the right thing, please come ask me, because I'd rather have you come and talk to me and say, hey, I found this code on the internet. I think I want to use it in my project. Is that okay? Let's talk about it first, rather than me finding out later on that you stole code that you shouldn't have, right? Because I have a lot of free time. I don't have any kids. Warner Hall is a 2-minute walk. I will go over there. I will report you and wreck you, okay? I don't care what you guys did what you did in undergrad, what you think is okay. Plagiarism is not cool, and we're definitely not going to tolerate it. And you'll see this multiple times. Okay, so my office hours will be on Monday and Wednesday, 1 hour directly after class. Open my office. If you need to meet me with another time, just come let me know. And so when you want to come talk to me, we can talk about implementing the projects. We can talk about the papers. We can talk about databases in general. And the one thing that I've noticed in my previous classes that people end up liking to do, which I don't know why, is they often come to me and talk about the relationship problems. And at first, I was like, all right, no, I'm not going to do that. But it's happened so many times, I'm actually going to be open to this, right? But I have no official training or qualifications to help you with your girlfriend or boyfriend problem, so take that with a grain of salt. But please, actually, this is true. If your girlfriend or boyfriend breaks up with you, please cry at home before you come to my office and cry, because that's not good for anybody. That was weird. OK. All right, so we have 2 TAs in the class. Unfortunately, they're not here right now and CMU, or actually even in the state of Pennsylvania for legal reasons. So the head TA for the course is going to be Joy Arulraj. So he's the one that's helping us build the database systems. He's helping run all the projects. He'll probably be your main contact when you have questions about the code. Right now, he's back in India because he had to turn himself in for like a 30-day bid for some accessory to armed robbery when he was an undergrad. So he'll be back in like a month or so, but you can't contact him now. Moo Lee is in a sort of weird, again, more relationship advice problems. Somebody accused him of fathering a child. I advised him to leave Pennsylvania, so he's currently in San Francisco, and he's unlikely to come back to Pittsburgh. So he's going to be helping out with all sort of the background stuff, the testing scripts, the utilitarian things. But again, the main thing is that if you have questions about your specific parts of the code when you work on your projects, Joy is going to be your main contact. Moo is not going to be able to help you. Okay? All right, so now let's talk about what all the assignments are going to be. So the first thing is that for every class, there's going to be one mandatory reading. And if you go look on the course schedule on the website, you'll see they'll be marked with a little yellow star saying that it's the mandatory or the primary reading for that day. So before every class, starting this Wednesday, you have to turn in a one-paragraph synopsis about the reading assignment. Right? So this is not me trying to check to see whether you truly understood the paper, or I'm check to see that whether you're making things up or whatever. It's really just sort of a forcing function for you guys to read the paper before we show up in class. So that way you're not sitting there and learning things for the first time. Right? This is a graduate level course, so it's supposed to be a dialogue between us to discuss all the different aspects of these papers. So the synopsis just really needs to be, again, really simple, one paragraph, 2 sentences that say what the main idea of the paper is, a sentence that says what system they're testing and they modified to check their methods, and then a sentence that says here's the workloads or here's the benchmarks that they used in it. It's just, again, to give you exposure to sort of the research papers in the database systems field. All right? And so there's an online Google form. If you follow this link here, that's where you can go and submit it, and it'll be timestamped to say when you actually submitted it. And so you're allowed to skip 4 assignments throughout the entire semester. I think in total there's like 24 papers that are mandatory or so. So you only have to read 20 of them. And also on the schedule as well, you'll see that there'll be the one marked with a star that says that's the primary reading, and then there'll be some additional ones that are optional, and those are obviously you don't have to read. I'll cover them in the lectures because I think they provide additional information or another perspective of the mandatory reading. But they may be things that when you go to do your final project, if you want to learn more about something that we covered in the class, then the optional readings will be there for you as well. Okay, and everything is on the website. You just download it and click it. Okay, so again, not to beat a dead horse, please do not plagiarize your synopsis. Do not find somebody else who wrote a paragraph about what these papers are, because other classes read, and other schools read the same papers, and they may have online synopses as well. Please do not copy what they wrote and try to pass it off as your own. Please do not copy what's in the paper and claim that, oh, this person's smarter than I am, therefore I dishonor them by trying to rewrite it in my own words. Do not do that. That's plagiarism too. Okay? And again, if you're not sure about what's the right thing, please read this or contact me. Okay? So now, the programming projects. So as I said, all the programming projects are going to be based on Peloton, which is our new database system we're building here at CMU. And again, I'll talk about more what makes this system unique or what's interesting about it next class before we get started. But the main idea is that it's going to be an in-memory database system that we've been developing for the last year or so that's based on Postgres. Right? And this is sort of the standard thing that everyone does when you build a new database system. And you'll see this throughout the course. They start with Postgres. Right? And so we'll provide more details in the next class on how to get started with the first project. Again, it's going to be a large code base that is going to be pretty complex. But the nice thing about it is we support almost as much as SQL 92 as possible. So you can start your database system up, open up a terminal, and start writing select queries to it and see that your thing actually works. Right, so this is a real database system. This is not a toy. And I think this would be something that would be really worthwhile for you guys to work on. OK, so for the programming projects, you're going to want to do all the development on your local machine. So unfortunately, Peloton only compiles and runs on Linux. We spent about a month last semester trying to make it work on OS X, but we just couldn't get it to compile. Okay, so all the development has to be done on Linux. If someone wants to go and be super motivated and try to get it to work on OS X, let me know. We can try to make it happen. But we spent a while. We can get it to compile. We couldn't get it to link. And so to get around this, we're going to provide you with a Vagrant configuration file. So like, we'll provide you with a Ubuntu virtual machine that you can then run on OS X or Windows or whatever. And you can do all your development inside of that. Okay? And then for the actual, when it comes time to do the final project, or if you want to do additional benchmarking to see how fast your implementation is for some of these projects, we'll have a cluster set up later in this month. You'll be able to log in and probably have more power or more RAM than what's on your laptop. So you can try larger data sets and try more complex things. We're super happy, super happy that MemSQL, which is a sort of a leading in-memory database startup out of San Francisco, donated all the machines that we're going to have for the cluster for you guys today. So we're super happy and super grateful for that. OK, so for the first two projects, these are going to be individual things. Or sorry, the first project will be individual. The second project will be done on a group. And so for these first projects, everyone's going to implement the same thing. So we'll tell you to implement a hash join for the first project, and then a B+ tree, a concurrent B+ tree for the second project. Right? And so that way we can actually check to see whether everybody has done the correct thing. We can benchmark you to see who has the fastest code. Right? But we're going to provide you with all the test cases and instructions on what you need to do. For the second project, we're going to do done in groups of 3. So we have 30 people enrolled in the class. So we'll do 10 groups of 3. And again, since all this, everyone's working on the same thing, we want to stress this enough. You can't stress this enough that you cannot be taking code from other people in the class. You cannot be taking code from random thing you find on the internet and try to pass it off as your own for these first two projects. Right? That's considered plagiarism. That's considered stealing. And I will report you. I'm in an argument right now with Warner Hall because I'm trying to let them list all the students that plagiarized in my class on my website for forever, and they won't let me do that. So I'm dead serious. Do not plagiarize, OK? For project 3, this is the open-ended one. This is sort of the final project for the course, right? So you be a group of 3 people, and you'll pick some project or some idea that you want to implement in the database system based on the things that we talked about, right? And the basic criteria for what I'll say, yes, that's an appropriate project, is that it has to be relevant to the things we talked about. It has to require a significant programming effort for all the people in the group. Right? You can't just have one dude hang out and write all the code, and then the other 2 people do nothing. Okay? And of course, you can't have, I don't want 2 groups picking the same topic. So if one group wants to pick, I want to implement a skip list, and no other group can pick the same thing, even though maybe they think they can do a better job. Right? We want to have a sort of wide scope of different topics. So you don't have to pick a topic until after spring break, which I think is like the first week of March. And then we'll provide you with some sample topics or some things that we think will be interesting if you can't think of anything your own. But I know there's a lot of PhD students in this course as well, so I highly encourage you to pick something that's actually relevant to your research. So not everyone here is doing a PhD in databases, but if there's something in your own research that you think you want to apply it to this course project, by all means do that. I think that's makes for some really interesting work. All right, so for project 3, there's going to be 5 deliverables that you're going to have to do that throughout the semester. So sort of like checkpoints as you go along the way to make sure things are working out OK. Oops, sorry. So the first thing is that after spring break, you'll have to do a 5-minute proposal in front of the class and say, this is our project. This is what we're going to do. This is how we think we're going to implement it. Right? This is basically just for you to figure out what exactly you're going to be doing. And I'll approve it and say, that's a good idea. Then about a month later, we'll have a checkpoint or a status update to the class. And again, this will be another 5-minute presentation where you basically say, here's what we've done so far. Here's some problems that we ran into. And here's how we think we're going to be able to finish. So now, when it gets timed at the end of the semester, there's going to be 3 things that's going to happen. So the first thing is that we're going to pair off groups, and then we're going to assign them to each other and have them do code reviews. Right? So this is a standard practice in industry now, where you have people look at other people's code and provide them feedback or suggestions or criticisms about what they did wrong, what they could do better, or what doesn't make sense. So I wanted you guys to get a feel for what this is like for this course. So you're going to be looking at other people's code and providing them with useful feedback to help them improve it. And I'll be grading you based on your participation in this process. So if you just say, yeah, this looks good, whatever, right? That's not helpful for anybody. Right? So we'll make this all hook up on GitHub and make it real easy for you guys to communicate and improve the quality of your code. Then in the final, at the period for the final exam, so whenever, I don't know what the date is yet, but when this course is assigned a final exam, we'll have like a 3-hour session where everyone will come and present the final status, the final update of their project. So this would be a lot more time. And so you want to include any kind of performance benchmarks or measurements that you did for your project. If you have a cool demo, that would be kind of nice as well. I'll cater this. But that's sort of the end goal is to present this thing and share it with the class. But the project is not considered done until you're able to provide us with a patch or a pull request on GitHub with your final project. Right? So we're not going to merge everybody's code in, because if you write something that runs on some esoteric hardware, we're probably not going to want that in our system. But we want to be able to merge it be able to merge it cleanly as if we could, or as if we did want it. So that means that you're going to have all the code review comments that came up in that feedback process. All that has to be fixed. You have to document everything, provide instructions on what your thing actually does, and have it as if it's a real deliverable you're going to provide us that we want to merge into the master branch of our system. Right? So this is not writing code for this one-off project just to get a grade and you're done, right? And then no one ever sees it again. We want you to write high-quality code, because this is what would be expected if you were actually working on at a startup or a database company trying to build a real database system. Okay? And again, we'll provide, I'll talk about later in the semester, what's all expected to make the final code drop. Okay? Now, we're also going to be having a final exam, and this is instead of having this on the final exam date, whatever the reading period is, this will be in the last class on a Wednesday, August 27th. So the class is only about an hour long, so it'll be an hour-long exam. But it'll be a long-form written short answer question exam where it sort of asks you to synthesize ideas of the topics that we talked about in this class and show that you have an understanding of the trade-offs and implications of the different techniques that we've talked about today. So it won't be true and false, it won't be multiple choice, it'll be short answer questions. Okay? So now the last piece is that we're actually going to be offering extra credit for the course as well. So as part of the Carnegie Mellon Database Group, we're working on a new online encyclopedia of database management systems. You can kind of think of this as the database of databases, right? And so it's sort of like a Wikipedia-style thing where it's, we want anybody to be able to come and edit it, but it's more structured than what Wikipedia supports. So we're going to be offering extra credit for anybody that wants to write an article about some database management system. It could be an academic one that we discussed in the class. It could be a commercial one. It could be a historical one that doesn't exist anymore, right? But the idea is that we want to build out this encyclopedia of all these different database management systems that have been around for the history. It's about 300 to 400 or so that I've counted. But there's no real good single source of what they did, why they were important, and how they implemented certain things. So the idea is that you would pick some system, you would write the materials for what it did, and then add it to our website, and you'd be cited as an author for it. So this is not writing like a Wikipedia-style essay. It's more semi-structured. So for things like concurrency control, there'll be a list of things you can select so that we have the same taxonomy across all systems. So you ever look at like Wikipedia, you look at see how they describe things. One article for one system will say it's 2PL this way, another one will say it's two-phase locking another way, right? We're trying to have a uniform sort of standard syntax and nomenclature across all these systems that make it easier to compare. So then we can say things like, show me all the multi-version concurrency control systems from the 1980s, right? And currently you can't do that in Wikipedia. So again, this is optional. This is extra credit. You're not required to do this. I'll talk more about it later in the semester as we get closer to actually launching the site. And again, please do not plagiarize these articles, because your name's going to go on it, right? And if someone sees that you took images, you took text from what they wrote and try to pass it off as your own, they're going to come back to you and complain, or they're going to complain to me, and then I'm going to complain to you. So again, please do not plagiarize. I don't care that the person wrote it better than you. You have to write everything in your own words, okay? I can't stress this enough. Okay, so here's the breakdown for the grade. So the reading reviews are just 10%. The 3 projects will be 70%, and the final exam will be 20%. Right? As you can see, I mostly care about the programming stuff, right? The final exam is just to make sure that you understood sort of what we talked about in the class. But I really want you to get out of this is be able to write code in a complex database system, right? And that's why we're placing this emphasis on the programming assignments when it comes for the final grade. And then we'll tack on 10% for anybody that does extra credit. OK? So the course mailing list will be through Piazza. Here's the link here. It's also on the website. Please sign up if you haven't already. We're going to use this for all the technical questions we have for about the projects. Right? So don't email Joy or I directly, because if you have a question about it's not compiling correctly, I'm getting this weird error, I don't understand, we want that all to be captured on Piazza. So if another student has the same kind of problem, they'll be able to go online and figure it out. And maybe not emails all. But any other sort of non-project questions about logistics of the course or other things like that, please email me and not the TAs. OK. So any questions about the game plan or roadmap for the course for the entire semester? Any questions about the expectations? Any questions about the assignments? Blank stares. OK. All right, so for the rest of the course, we're going to do an abridged history of databases. So this material is derived from two papers that are listed on the website. The first is an article written by Mike Stonebreaker called "What Goes Around Comes Around," and he wrote this as an introduction to what is called the Red Book in the database community. Basically, it's a compendium or a collection of important database systems or database papers. And so he has an introduction, talks about basically the history of databases up to around 2006. And then the second paper is called What's Really New with NewSQL. And this is the article that I wrote with Matt Aslett, who's an industry analyst out of London. And this basically picks up where they left off in 2006 and talked about sort of these new NewSQL systems that have been around for the last 5 years or so. OK? So let's start from the beginning. So one of the aspects that I think that is important to understand about databases is that a lot of the issues that they had in the original systems from the 1970s are still really relevant today. Right? It's just the scale of things, the scale of the problems has changed. Right? So dealing with disk I/O, dealing with lock contention and things like that, all of those are the same problems that they had back then, but now we're just doing it with 100 different cores running on the same machine, dealing with much larger data sets because we have the internet, we have a lot of more concurrent users, right? So all the same things that they worried about back then, we still have to worry about today. And actually what's really striking is when you go read about the first database system, a relational database system that IBM built, System R in the 1970s, they explored a bunch of ideas that they thought were interesting, but they ended up abandoning because they couldn't make it work with the existing hardware. But now there's companies that are basically adopting the same ideas from back then, and now it works, and now it makes sense because the hardware is able to support it. Right? So one of the key things is, like, one example of this is they had this idea in the 1970s of taking data from related tables and combining them together and storing them on the same page. Right? You have a customer table, you have an order table. You take all the customer's orders and you pack it in on the same page as where the customer is, right? And then it didn't work because it was too difficult to manage, too difficult to implement. But now Google does this in Spanner with column families, or in the protocol buffers. They pack things together that are related. So now it's only one fetch to go get the things you need, right? So a lot of these same things that they worried about then, we still worry about today. Another interesting thing is that I feel that the debate that's going on, or if you want to call it that, between the SQL versus NoSQL crowd is reminiscent, or basically the same debate that existed in the 1970s between the relational model people and the network model, the codicil people. And I'll talk about what codicil is in a second, right? But basically, the NoSQL guys are saying, well, you don't need transactions, you don't need joins, you don't need the relational data model, right? You write everything as a key value store or as JSON, that's better, right? It's the same thing that they said back then, and these guys lost because none of you probably ever heard of codicil, right? And now 2016, all the NoSQL guys, except for MongoDB, are adding back in all the stuff that they said they didn't need. They're adding back SQL, right? They're trying to add back transactions. So again, a lot of the ideas that we'll be talking about are not necessarily new. They're just new adaptations of them to work on modern hardware. OK, well, let's talk about the very beginning. So the very first database system that was ever developed was this thing called IBM IMS, Information Management System. Right, so IBM developed this for the federal government to keep track of all the parts and suppliers for the Apollo moon missions. Right, so they were essentially working for NASA before it was called NASA. Right? And so IMS, it still exists today. It's actually, I think it's one of the #1 bestsellers for IBM, or it makes the most money for them, right? Because they have all these banks that picked it up in the 70s and still have to maintain these systems, over the years. I think a lot of the ATMs, the back end of the system, actually still runs on IMS, right? And so the IMS is based on sort of 3 key ideas. So the one is you're going to have a hierarchical data model. I'll show what that means in a second. You're going to have programmer-defined storage layouts for the actual collections of data. So what that means is you would have, say, I have 2 collections of data. Think of them as tables. You would say, I want this table to be represented as a B+ tree, and this table to be represented as a hash table. And then once you did that, once you made that choice, then IMS would expose a certain API to you that you then use to make queries against those collections of data. Or so that meant is if you pick, say, like you pick one to be a hash table, you couldn't run range queries on it, right? The other weird thing about IMS is that it had this tuple at a time interface, or you'd have to write your own procedural code to traverse the data structure and access tuples at a time. Whereas in a relational model, it's based on like a bag algebra, a set algebra. So you can deal with large number of tuples really simply with easy queries. So here's what the hierarchical data model looks like. So we have a simple schema here. We have a parts supplier database. So we have an upper collection here of suppliers. So these are the businesses that sell a certain item. And then you have another collection of parts. So these are the items that they sell. And so the way you would instantiate a database in a hierarchical data model based on this schema is that you would have the first collection here, and that would have all the supplier information. But then for each of them, they're going to have another data structure for all the products or parts that they sell, right? And so the way you would say, if you want to run the query, say, find me all the suppliers that sell batteries, you would have to write a bunch of for loops to traverse the suppliers, and for each one, look at all their parts one by one by one, right? So there's a couple of problems with this, obviously, right? So one, that's a pain in the ass to write, so you have to write really complex queries. But then we also have duplicate data, right? So we're going to store that this guy sells large batteries and this guy sells large batteries multiple times for each of those suppliers, right? Because there's no way to sort of maintain relationships between these things. So one is you're going to have duplicate data, right? And then there's no independence between the physical structure of the database and the logical schema. Remember I said you have to specify whether a collection is going to be a B+ tree or a hash table. So that means that if you pick a hash table and you realize, oh, I actually want to run range queries on these things, I don't want to use a hash table, I want to use a B+ tree, you have to dump the database out and then load it back in, right? And that sucks. That's a big pain. It's a big waste of time, and it's a lot of overhead. So this is around 1968 is when IMS came out. And like I said, it's still being used today in a lot of different enterprise settings. So around the same time after IMS, there was a movement called Codicil, where a bunch of people that were working, or a consortium of people that were working on COBOL programs got together, and they basically came up with a standard API or standard interface for how COBOL programs will access a shared database. And the basic idea of how Codicil works is that it's going to have that same tuple at a time query interface that the hierarchical model had in IMS, but it's going to use what's called a network data model. And if you don't know this person here, this is Charlie Bachman. He was sort of the lead proponent of the Codicil group, and he won the Turing Award for databases, I think in like 1971 or 72, which I think he's still alive. But nobody uses Codicil anymore. So here's how it basically works, is that you have sort of like this graph structure where you have the different collections of data. So now you can say, here's the suppliers, here's the parts that they're going to have, and then you have this cross-reference relationship that combines the supplier part with the part, and say, here's the things that the supplier is supplying. And the weird thing about it is that you have these additional sets that correspond, that represent the relationships between, I don't use the word relationship, the existence of different elements of this set with this set. Right? So you have to instantiate these additional data structures here to say that there's a linking between them. So now, if I want to run this query that says, find me all the suppliers that supply large batteries, I have to loop through one by one in these nested for loops, look at all the suppliers, look at all their elements in the supply set, then I come down here and get all these, and then in a separate thread, I go to the parts and traverse it down to get them, and I mash these things together. And you're writing, like, essentially, again, nested for loops to do this. You're not writing a declarative language like SQL to perform this query. You have to write the exact steps of how you want to traverse this network here in order to get to the answer that you want. Oh, it didn't show up. So the first problem is that you're writing complex queries to do really simple operations. The second problem is, if this supplies or supplied by sets, if these things get corrupted, then both of these tables get corrupted because you have no way to link them back and forth. Right? So there's no independence at all, again, of the logical schema with the physical representation. So around the same time that Codicil was coming out, there was this guy called Ted Codd at IBM Research in New York, in Watertown. And he was a mathematician. He wasn't a computer scientist. And basically, he was walking around IBM, and he saw all these programmers were spending their time rewriting or over and over again these IMS or Codicil programs every time the database changed, right? So what happens is, because we're writing all these for loops to tell the database system how we want to walk through things, if the layout of this thing changed or this changes, I have to go back and now change all my code to be able to walk through it correctly, right? And that's really expensive to do. And it's a huge waste of time. So what he came up with was this abstraction where the logical structure of the database and the physical structure were completely decoupled. And rather than having these nested structures or these hierarchical structures, these networks and things like that, you would have these simple abstract objects called relations that would represent the data for a single entity in your application. And then you can maintain the relationships between them directly within the data and don't have to have these extra sets on the side. The other key thing that Codd came up with was, again, rather than you writing your own for loops to loop through and find the thing that you want to write at a high-level declarative language. You want to tell the database system what answer you want it to compute and let the database system figure out the best way to do this. Right? Sort of like the same idea in compilers, right? Nobody writes assembly anymore unless you really have to. But you can write in C, this is essentially what I want to happen, and then the compiler will figure out the best way to optimize your code and compute the answer you're looking for. So then again, the other key thing is that the actual how the data was stored on disk or on memory was completely independent of the logical schema. So no longer you'd have to specify, I want this table to be a hash table and I want this one to be a B+ tree. You just say, I want these tables with these attributes, and then the database system makes the best decision of how it should store it. And now, because you're dealing with it at a logical level in a declarative language, if the underlying storage layout of the data changes, you don't have to go rewrite your queries on top, right? Everything just works. So again, I don't have to explain what the relational model looks like, but basically now we have that same parts and supplier database. Now we have relationships between all these things, and we don't have to worry about traversing them. We don't have to worry about set inclusions and things like that. We just deal with these abstract objects in SQL, which is really nice. So in the 1970s, Ted Codd came out with his paper, I think it's 72, and said, here's how we really want to have databases. We want to use a relational model. We want to have this abstraction. We want to write our queries in high-level languages, right? But IBM was still making a killing with IMS, and the Codicil guys were off doing their thing. So it was like basically 2 or 3 groups in California got together and took Ted Codd's paper and actually tried to make it work, try to build a system, a database system, that implemented the relational model. So the 2 most famous ones are System R out of IBM Research in San Jose, and then Ingress, which was a project out of the University of California led by Mike Stonebreaker, who won the Turing Award this year, and who was one of my advisors when I was in grad school. they basically were building their own versions of or database systems based on the relational model. Around the same time, Larry Ellison was founded the Oracle Corporation, and he would actually end up calling the IBM guys on the phone all the time and ask them what did their database system do. They would tell him, and then he would go implement the same thing, right? Again, here's another motivation why you should take this course. Has anybody heard of Jim Gray? Right, Jim Gray was a famous database guy at IBM, helped build System R. He won the Turing Award in the 90s. He got lost in sea in like 2006, 2007. People loved this guy so much as when his ship went missing off the coast of San Francisco, they moved satellites around above to try to find him, right? So he won the Turing Award. Mike Stonebreaker, he won the Turing Award. Larry Ellison is like the 5th richest man in the world, right? This is why you should take database systems, right? Okay, so Ingress they commercialized it. IBM never commercialized System R, and Oracle went off and it did their thing and became a real company. So then around the 1980s, in the early 1980s, what happened was, although IBM never put out System R because that would cannibalize their sales of IMS, they eventually saw the light and saw that the relational model was going to win. So they ended up building a new database system with bits and pieces of System R called DB2. So this got released in 1983, but when DB2 came out, it announced that it was going to use SQL as the declarative language. Because in the 1970s, it was SQL versus this other language called Quell. So SQL came from IBM, Quell came from the Berkeley guys. And they're basically, if you look online, they're roughly equivalent. They more or less do the same thing. Stonebreaker says Quell is easier to read. I disagree, but whatever. So when IBM came out, since they were sort of the king of enterprise software at the time, they said our new database system is use the relational model and it uses SQL. So essentially SQL became the de facto standard. And Oracle, since they were copying what IBM was doing all along, they supported SQL. So waha, they were there at the right place at the right time, and they had a relational database that supported the standard that IBM was pushing. Around the same time, about 85, 86, a bunch of other what I call enterprise database systems or relational database systems came out in the market. Informix and Sybase are sort of probably the two most notable ones. And all of these have connections with Mike Stonebreaker. Ingress sort of floundered 85, 86. And then he went back to Berkeley and he built the next project called Postgres, which is what everyone knows about today, right? It's called Postgres because it's the thing that came after Ingress. And Oracle sort of continued their dominance in the relational database world. So it's funny because IBM DB2, all these systems are obviously still available. Sybase got bought out by SAP. They're kind of not really as big as they used to be. And then Informix got bought out by IBM. I think it's still there, but again, if you're building a new startup, you wouldn't pick those systems. You would use something more modern. All right, so then in the late 1980s, there was a new movement that came along, sort of like the NoSQL guys of today, where they basically said, well, the relational model is not what you want to use when you're writing object-oriented applications or using an object-oriented programming language like C++, right? Because inherently in C++, you're working with objects, and when you want to store them in a database system, you have to do this work to convert them from an object into relations. And this is very cumbersome, this is very slow, and what you're better off doing is just having a tight coupling between the database system and your programming language, your programming environment, so that you can write objects natively and store them natively in the database system. And you don't have to worry about splitting them up and joining them back together across multiple relations. So there was a bunch of systems that came out in the 1980s. You've probably never heard of them because they don't exist anymore. Or if they exist, they're like barely used at all. But a lot of the techniques that they came up with at the time are actually used in some of the NoSQL systems and relational database systems today. So basically, you can think of the object model as the same as a document database or a JSON database or an XML database. So to give an example of how the object-oriented model works, so say this is your application code. You have a class object, or you have a class that defines a student. A student has an ID, a name, email, and then a list of phone numbers. So if you had to implement this in the relational model, you would have a student table, and then it would have a foreign key reference or a foreign key reference from a student phone table that had the student ID that mapped it back to the student that has that phone number, right? So and now when you actually instantiate the database, you would have a sort of layout like this. You would have one student record, and then you would have all the phone records, and they would sort of correspond to these fields here. So now if you wanted to instantiate this object in your code, in your application code, you would have to do a join between these two tables to get all of the get all the phone numbers for that particular student. Or you have to do two separate queries, which is slow, because that's two round trips back and forth between the application and the database system. So the object-oriented guys say, this is terrible, you don't want to do joins. What you really want to do is just, when you instantiate an object, store it directly in the database system like this. So now when you say, I want to go get a single student, you go fetch that one record, and you get all their phone numbers as well. Right, but this sort of has the same problems that we saw in the hierarchical or the network model, where you're going to have to write complex queries to do things beyond just getting one object, right? If you want to say, find me all the students that live in this location and have this other, these types of phone numbers, you're going to have to write procedural code, again, nested for loops, to go iterate through all the different tuples that are different objects and find the answer you're looking for. And now that means if the schema changes of your object, all your code's going to break, all right? And then the big thing, I think, was the big downfall for these guys was that there was no standard API for how to do this, right? All the different programming languages or all the different object-oriented databases all had their own APIs, all had their own ways for doing reads and updates and things like that, right? And so if you wrote your application for one database system, you could not easily port it to another. Now you may say, oh, SQL is the same thing because it's all these different dialects of SQL, and you can't take your Oracle application and make it work immediately on Postgres or MySQL. That's true, but it was even more worse than these guys here, right? And now you sort of see why the NoSQL guys are slowly adding back SQL, right? Because the Cassandra is a big NoSQL system. They have this dialect of SQL they call CQL, but it more or less is SQL. Right? All the Hive and other database systems built on top of the Hadoop infrastructure, they're all adding support for SQL. All right, so that got us through the 1980s. The 1990s was pretty boring in the world of database systems, right? No workload really changed. It was sort of before the internet got really big. There's no, the hardware got better, disks got better. But there was no sort of major change in how people use database systems in applications, right? So the only sort of, I consider the notable things that happened was Microsoft made a deal with Sybase to port their code to make it run on Windows NT. And then they essentially just changed the name of it, and that became what's known today as SQL Server. And it's funny because SQL Server actually is what I consider is, they're adding a lot of new ideas that I think are pretty cool. Whereas the original code Sybase is somewhat stagnant. Some Swedish guys took there was an earlier system called MSQL, which is a precursor for MySQL. So the guy that wrote MSQL sort of threw all the code away and started over, and this ended up becoming what was known today as MySQL. And then for Postgres, they had went and formed a company called Illustra that eventually got bought by Informix and sort of fizzled out. But then some grad students at Berkeley took the original Postgres code that they developed in the university and added support for SQL, because again, before it supported Quell, because that's what Stonebraker really liked. So then they added SQL, made it open source, made it available, and then people actually started using it. And now Postgres is, I think one of the best open source database systems that are out there today. But again, there's nothing really major beyond these three things happened during this time. So then we get to the 2000s. We hit the internet boom, right? The dot-com days. So a couple of things happened. The first is that, again, the number of concurrent users trying to access the database grew significantly, right? And the size of the data sets grew significantly as well, right? Where it used to be maybe only a few handful of major enterprises had what would be considered a large database. Now you can do a startup and immediately have a large database overnight. So at the time, the early 2000s, you had all the major database companies that we've talked about so far, right? You had the Informix, you had the Oracles, the Sybase, the IBMs, the Teradata's, things like that. But these systems were closed source and very expensive and very heavyweight. So they weren't quite ready to be able to support the large number of users you would have in an internet application. And the open source systems like Postgres and MySQL in the early 2000s, they were still pretty young and still not, I would say, battle ready for some really hardcore applications, right? So some people did some things to make this work was to write their own middleware to scale out a bunch of single node databases and have them appear as a single logical database. So eBay did this. Obviously, Facebook has the largest MySQL cluster that's doing this. Google did this. So they sort of took these simplistic databases and they built more complex, support for more complex operations or scaling out on top of them, right? Again, the major players were simply too expensive to do this. The other big thing happened in the 2000s was the advent of special purpose data warehouses, right? And so these are databases that are not meant to be updated through transactions. These are meant to be databases where you store all the data that you've collected from your front end in this back end and do all your analytics and analysis on that so that you don't slow down the sort of the front end system that's serving customers. And so the big thing about these systems, or the major thing that came out of these systems, is that they were designed from the ground up to support OLAP queries efficiently, right? And rather than being a general purpose system, sort of what Oracle tries to be or DB2 tries to be, they had the internals are written such that they can run analytical queries more efficiently. So Netezza is probably a bit earlier than what I would consider the group for these guys, but this was a FPGA-based system that IBM bought. I say of all of these, the only one that I think that was sort of truly novel and really groundbreaking was Vertica. Right? But all these guys have been bought. Netezza got bought by IBM. Parexel got bought by Actian, which is the version of Ingress. Vertica got bought by HP. Right? And one of the big things, and one of the big ways that these systems were able to do much better than the incumbent systems is that they supported the decomposition storage model, or DSM. So essentially, they were column store systems. So rather than storing data in sort of a row-oriented format, as you would learn in an intro class, they're going to break up the attributes and store all the columns contiguously in memory or on disk, so that when you run an analytical query that only has to access a small number of those attributes, you're not going and reading a bunch of rows or a bunch of attributes that you don't care about. And the performance difference you can get in a column store versus a row store for analytical queries in a data warehouse is massive. It's enormous. I had a friend who was a sales engineer at Vertica, and he went down to Australia to visit like a telecom, and they had some query at the end of the month that would process bills and things like that. It would literally take days. One SQL query would take days. They loaded everything up in Vertica, and it got down to minutes, right? This is huge. This is a big game changer for the database world when these specialized data warehouses came out. So then we get in the late 2000s, and this is when the NoSQL guys sort of show up. And they had all the same problems that the early .com companies had, where the sort of existing databases were not be able to scale out and scale up and support the large number of concurrent users that they needed to have. So they took a different route. They actually went and just wrote their own database system. And they made some sacrifices in order to speed up development, make it easier to build these things by giving up on transactions and joins and other things like that. Right? And then they later said, this is a feature, you want to do this. So the key thing about the NoSQL systems is that most of them are non-relational. Right? So they're not going to be using the relational model. They're going to be storing it as documents, as key values, as column families, or things like that. They're going to be storing things without support of full ACID transactions. They're going to be using custom APIs in some cases instead of writing SQL. But the nice thing about the NoSQL guys is that they are usually most of them are open source. And a lot of them that started off as closed source eventually became open source. Whereas a lot of the data warehouses, except for one of them, are still all closed source today. They would argue that part of the reason they didn't support the relational model, or part of the reason they didn't support transactions, is that they weren't really worried about correctness in their operations. They were worried about high performance, availability, and scalability. Right? It's not good that it's great that your website can execute transactions correctly, but it's not all the time. But it's not great if you can't run anything at all. Right? If you have sort of the Friendster problem, where every page load takes a second because you're just hitting the database super hard, that doesn't help anybody. So they gave up all those things in order to be able to scale up and support the large number of users that they had. All right, so now we get to the 2010s, And this is sort of the rise of the new SQL systems. And I have to fully admit that I was one of the first proponents of this movement, if you want to call it that. So the system I helped build when I was in grad school was called HStore, which then later commercialized as VoltDB. If you read the Wikipedia article on NewSQL, you'll see that HStore is listed as one of the first NewSQL systems because it came out in 2008. I wrote that, so I can say whatever I want. So the NewSQL systems, the basic idea is that they wanted to have sort of the same scalability that you can get from a NoSQL system, right? But without having to give up the relational model, without having to give up transactions, right? And the way they're going to do this for the most part is they're going to be mostly in memory, and they're going to be distributed. So they'll scale out your database or shard your database across multiple nodes so that the aggregate amount of RAM across all those nodes is enough to store your entire database. So now if you don't worry about disk anymore, you can forego a lot of the legacy components that you would have in a traditional relational database system because they're going to slow you down and help prevent you from performing and scaling up. So again, in the NewSQL world, they're all going to be relational. They're all going to be SQL. For the most part, they're actually, I say for all of them, they're going to be distributed. The downside is most of these are going to be closed source. I think VoltDB and HStore and Gemfire are probably the only open source ones. It is what it is, but that's their prerogative. All right, so what's next? What's coming after NewSQL? The next major trend, the next major, I think, category systems that are being developed in the upcoming years are what are called hybrid systems, or HTAP systems, hybrid transaction analytical processing systems. And the big idea of these systems is that, again, they want to be like a NewSQL system where they want to support fast transactions that are ACID and correct and high performance. But then they also want to do some of the analytics that you could do in a data warehouse directly on the data as it arrives inside the database system. Right? So normally what happens is the typical setup now is you have sort of like a NewSQL or a front-end database system that's executing all your transactions. And then over time, you stream updates to your back-end data warehouse, do all your analytical queries on that back-end machine, and then send updates to the front. Right? So you see this a lot in like internet gaming. So you have like, say your Farmville application. You have people clicking on things, and you're changing stuff in the farm, and all those are transactions that are getting recorded in the system. And then they stream those updates to a back-end data warehouse where they run some kind of analysis or machine learning models to figure out some way to make you buy virtual goods more easily, right? And then they send those updates to the front end, right? So there's sort of this round trip time of when the data shows up to when it gets sent to the back end warehouse, and then it's processed and then moved back to the front. So in an HTAP system, they say the idea is that as the data comes in, you can run the analytical queries that you would normally run in a back-end data warehouse directly when it arrives. So you reduce the latency of being able to come up with actionable information directly in the front end, and then help you sell stuff more quickly or whatever you're trying to do. So this is sort of the major, I think, the trend that's coming out in database systems now. So there's not that many of them that actually can support these kind of things. So MemSQL is probably the major one, along with SAP HANA. And again, we'll read papers from the HANA guys and the Hyper guys as well. So Hyper is an academic system out of the Germans. Just1DB is a closed source system out of, I think, London. But there's not that much information about that. But again, the basic idea is, again, you're doing transactions and analytics on the same machine. Now, this is not saying that the data warehouse is going to go away, because you're still going to have to use it as sort of a single site or a single source where you want to store all the information from your front-end silos. But again, some of the analytics that you would normally have to run on the back end, you can now directly run on the front end with these guys. So most of them are distributed. Most of them are shared nothing. Most of them they're all relational and support SQL. And then most of them, as of 2016, are closed source. OK, so at the end of every lecture, I'm going to try to have some parting thoughts of sort of the nuggets of wisdom for you guys to sort of walk away and think about. I say the main thing that you should understand about the history of databases in the last 30 or 40 years is that a lot of the good ideas, or all the good ideas, don't come from a single source, meaning they're not just coming from academia, or they're not just coming from industry. They're coming from everywhere, right? And the cool thing about database systems is that there's all these different organizations or groups of people working on building on new systems and coming up with new ideas. So you have academics like researchers, us here at CMU, doing stuff, But then you also have major companies like IBM, Oracle, and Microsoft doing stuff. But then you also have a bunch of little startups with their own little systems as well, right? So all the new ideas that are out there are coming from all these different sources. Typically, what happens is that a lot of them come from academia, but they don't end up, since most academics don't build a full system, they just have these little prototypes and they write the paper, and then some other company will pick it up and use them. But I think we're trying to change that here with our own system. IBM was, I consider, to be the vanguard, or the leading database system company in the 1970s and 1980s. A lot of the early ideas come from what these guys came up with. Right? They had one of the first distributed database systems. They had one of the first in-memory database systems. I don't think it's that way anymore. I think the real trendsetter is Google. Google does not release very many papers, but when they do, they usually have a big impact on this research area. They don't open source anything either for the most part, so that's kind of disappointing as well. But it is what it is. Oracle is always, in my opinion, about 5 years behind from what you could consider the state of the art. No, I don't mean this in a derogatory sense. I mean, they had the largest customer base in the world, right? They have a very complex database system that's been doing quite well for them the last 30 years or so. So you have all these legacy customers. You just can't come up, some academic writes a paper or some startup comes up with an idea. You don't want them sort of shooting from the hip. Just have one guy in his basement writing that new piece and adding it to this large complex system, right? They have a very, very challenging testing process, and you have to go through a lot of steps to prove that any new thing you want to add to the Oracle system is safe and won't degrade everybody else's performance. So again, they get a lot of ideas from other places, and then usually 4 to 5 years later, it'll come out in the real piece. Microsoft has actually been doing some really cool stuff in SQL Server, and they will actually read a lot of their papers in this class. I consider some of the stuff they've been doing, the database research group out of Microsoft Research, that gets added actually to the SQL Server product is really, really, really cool, really interesting. So the other major takeaway I have for you guys is that the relational model essentially has won the day for operational databases, right? So no one's going to write, eventually all the NoSQL guys will add back SQL. And if you were going to build a new application today, you'd probably want to use SQL, right? You probably would not want to use some proprietary API that may change over time. In the case of data warehouses and analytical systems, we're not quite there yet, but essentially SQL is going to win that over too, right? Hadoop came out. People realized writing MapReduce programs was a bad idea, so they built SQL layers on top of MapReduce. And then Spark has come out, and now they're showing that how most of their customers are writing their queries against Spark SQL and not writing using the Spark API. So eventually this becomes the de facto standard as well. So sort of like in the beginning, people didn't like it, then people liked it, and then now people don't like it, and then they're going to like it again. And I really think for the rest of my life, this is probably going to be the case. SQL is going to be the standard API that everyone's going to use for databases. OK, so that's it for today. So for next class, we're going to start off talking about, again, more introduction information about in-memory databases, what they mean, what changes in the architecture of a database when you assume everything's in main memory versus assume things could be on disk. And then we'll introduce you to what you're going to have to do for project 1. And we'll discuss the system, discuss the expectations, and discuss how to get started in that. And so as a reminder, the first reading review for the first mandatory reading is due at 12 p.m. on Wednesday. It's an easy read. It's actually papers from actually 1992. So you would normally think, oh, well, that's almost 20 years ago, or over 20 years ago. How is that still relevant? But what you'll see is a lot of the things that he discusses about here's what a main memory database is all about, here's the things you have to worry about, are still relevant for the things we're talking about in this course today. So, all right. Any questions? All right, if you haven't, there's a sheet going around. I don't know where it is. There's a wait list and the enrollment list. Put your initials now next to it so I know you're here. And we'll do it again on Wednesday. All right?